SwayamPrabha. Digital India. Educated India.
Again a two-dimensional problem. Only thing is the two dimensions, one will be space and the other will be time. So, it is an unsteady problem, and spatially it is one dimension and time is the other. So, you have to learn to think of time also as a dimension. Okay. So, this problem is called the Rayleigh problem, and this is the thing. You have a plate here, this is the y direction and this is the x direction and this is the z direction. So, this is the plate. The plate is in the xz plane. Okay. So, you have a plate which is infinitely long, okay, extending to infinity in the x and z direction, and there is liquid above this plate which extends to infinity in the y direction. Okay. So, you have liquid extending to infinity and the plate is liquid is extending in the y direction to infinity, the plate is extending in the x and z direction to infinity. We are interested in asking what is going to happen to the liquid when I suddenly move the plate at a constant velocity u naught. So, I will move the plate is at rest initially, okay, and suddenly moves in the x direction, okay, at a constant velocity u naught. So, physically what do I expect? When this plate is moving, the momentum of this plate is going to be transferred to the liquid next to it, it will drag the liquid next to it, and away from it the liquid will be stationary. As you keep waiting for more and more time, this momentum is going to diffuse in the y direction and the effect of the movement of the plate will be found by the liquid layers further away from the plate. Okay. Initially this liquid layer close to the plate will move. After some time that layer will drag the liquid layer above it. So, after some more time it will drag the liquid layer above it. Okay. So, that is what we expect, because it takes some time for the momentum to diffuse. Okay. So, we are looking at a problem here where the velocity component that we are interested in is only going to be in the x direction. Okay. So, only one component of velocity, that is the x component, okay, and because it is extending to infinity in the z and x direction, there will be no variation in those directions, but there will be variation in the y direction. The y direction goes to infinity, far away the liquid is stationary, velocity is going to be 0 here, velocity is going to be u naught here at the plate. So, there is going to be variation in the y direction. Okay. The other important thing is, as far as pressure is concerned, there is going to be a hydrostatic pressure gradient. Okay. There is going to be a pressure difference in the y direction, but that is not the direction in which the flow is occurring in the x direction. So, although there is a pressure gradient, the pressure gradient is in the y direction, but does it affect the flow in the x direction? Okay, those are some small things you have to understand. So, we have the pressure gradient in the y direction due to the hydrostatic head. I am calling it hydrostatic because as far as y direction is concerned, there is no flow. Is actually flow is there in the x direction. So, this does not influence the flow in the x direction. You understand? Pressure here is going to be more than the pressure on top because of gravity, rho g h. But at this plane pressure is constant, at this plane pressure is constant, at this plane pressure is constant. So, at every plane there is no pressure difference. Only reason why the liquid is moving is because this plate is moving. This plate is moving, it drags this liquid after let us say in 1 second. After 1 minute, this liquid will drag the other liquid on top. So, the velocity is going to propagate, the momentum is going to propagate. Okay? So, that is the idea. So, clearly what are we interested in? We want to find out u of y comma t. This is what I mentioned. One spatial direction, the only spatial direction is y and time is the other direction. So, you want to find out how the velocity changes with y and t. Okay. And if you do the simplification of the Navier-Stokes equations like we have done in the past, only 2 terms are going to contribute in that equation, and that is, if you simplify the x momentum equation, what you get is rho du by dt equals mu d square u by dy square. I am going to leave this as an exercise for you to do. You write down the complete x momentum equation and then you have to justify why all the other terms are dropping off, okay, like we have done in the past, and then you will get this equation. Because we have done this several times, I am not going to do it again. Okay. So, we basically have to simplify it by neglecting terms which are not important. This is obtained by neglecting terms which are not important or basically 0. Oh, maybe I can do it, it is not a problem. Rho times dou u by dou t plus u du by dx plus v du by dy plus w du by dz equals minus dp by dx plus mu d square u by dx squared plus d square u by dy squared plus d square u by dz squared. Okay, that is your x momentum equation. And now, okay, the easier one is there is no velocity in the y direction. Okay, therefore, this goes to 0 because v is 0. Similarly, there is no flow because it is infinite in the z direction, this goes to 0. There is no pressure gradient in the x direction because at every point at the same height there is no change in the x. Okay. Here it is some value at the same y location, there is no change. So, pressure value is the same, it is hydrostatic. So, dp by dx is 0 and again infinite in x, infinite in z, so it goes to 0. Here again u is not 0 because I need u, but I am saying there is no change in the x direction because it is extending to infinity in the x direction. So, this is 0, this guy is 0. Okay. So, the only two terms which are remaining are this term and this term. We have written the simplified equations, and you note that this is a linear equation. Okay. I need to solve this subject to some boundary conditions. Only thing is, now in the y direction the extent is infinity. So, what will be the boundary conditions? At y equals 0, u is equal to u naught, because of the no slip condition. The liquid velocity will be same as the plate velocity. Okay. And at y equals infinity, what will u be? 0, because so far away it does not feel the effect of the liquid of the plate moving. Okay. So, velocity is 0, and I need an initial condition at t equal to 0, u is equal to 0. The plate is at rest initially. Okay. The plate is at rest initially, it does not move, and therefore, the liquid everywhere the liquid is stationary. So, at t equal to 0, because nothing is moving, and at suddenly I start moving this plate. So, the entire liquid is going to be at rest. This is for all y, and this is for all t, this is for all t. So, u is a function of y and t. I am specifying y, therefore, this is valid for all t. For all t, this is going to be 0. For all t, this is going to be u naught. At time t equal to 0, for all y, velocity is 0. Okay. So, when I fix 1, the other variable is changing, correct. So, u of t comma y, so t is fixed. So, everywhere the liquid is stationary. That is the point we are making. Okay. So, that is good. So, I have the boundary conditions and this, and now I am ready to solve, and you notice that this governing equation is the linear equation. Okay. So, and you also notice that there is only one non-homogeneity here, u naught. Okay. So, this is a linear PDE with one non-homogeneity. The point is, one of the variables is time and the other variable is y, which extends to infinity. So, in the earlier problems that we did, the spatial extent which we were interested in solving, the spatial extent was finite. It was going to 0 to L, 0 to R, things like that, 0 to H. Now, in the spatial direction, it is going to infinity. Okay. So, typically when you have problems of this kind, you will use things like a Laplace transform or a Fourier transform. Okay. So, the standard methods for solving this kind of equation or Fourier transform. These are the standard methods. So, what do you do in Laplace transform? You use the Laplace transform and you will convert it to an, you will integrate out in the time direction. You will convert it to an ODE in y. If you use a Fourier transform, you will integrate out in the y direction. Okay, and you will convert it to an ODE in time, and then you can solve the ODE using the first principles. The whole idea of using this transform is to convert it into ODE, solve the ODE and then use a inverse transform to find the solution. That is the general idea. Okay. So, that is what we normally do in Laplace transform. We integrate in time and get an ODE in y. We solve this ODE and then use an inverse transform, okay, to get the solution. What do you do if you do the other one? In Fourier transform, we integrate in the y direction, get an ODE in time, solve the ODE, use inverse transform to find solution. Okay. That is basically what you do. I mean, you have done Laplace transforms in a course like process control, where you convert the ODE to an algebraic equation, right. So, basically when you do a transform, what you do is your ODE you make it algebraic, if it is PD you make it ODE, or you can do Laplace transform and Fourier transform, convert it to algebraic and then do inverse. So, that is the whole strategy, okay. But we are not going to do either of this. So, I am not going to spend too much time on this studies today. Maybe we will have time, we can look at how to do with Laplace transform on Fourier transform, but I am mentioning this to you because whenever there is a problem which is extending to infinity in the spatial direction, people use Fourier transforms, okay. And of course, in time is going to infinity, you start at 0, it goes to infinity, so use Laplace transform. Spatially you can go from minus infinity to plus infinity, so you go for Fourier, and time goes from 0 to infinity. You start today is 0, you do not go to minus infinity, you can't go back in time. So, we are going to use another method. So, I can use Laplace transform and Fourier transform only as long as my equations are linear. If my equations are non-linear, I cannot use Laplace transform and Fourier transform, okay. So, I am going to talk about another method which is basically called the similarity transformation, how to use similarity transformation to get a solution. The advantage of that method is I can use it for non-linear equations also, whereas Laplace and Fourier are basically restrictive only for linear equations, okay. So, these methods can be used only for linear equations. A third method, which is called the similarity transform, can be used for non-linear equations also, okay. So, that is the advantage of going for the similarity transformation, okay, because if I have a non-linear equation I cannot use this. So, now I mean it is not that you can always use similarity transformation, okay. You can use similarity transformation only for some class of problems, and I want to discuss a little bit about when we can possibly use similarity transformation, what the idea is. The basis for determining whether I can use similarity transformation or not is basically coming from the concept of making an equation dimensionless. Okay. So, when I make an equation dimensionless, I mean you are used to using characteristic scales for making an equation dimensionless. I mean we have done that in several problems. Okay. So, we need to use characteristic scales which are arising normally in the problem, and these are usually parameters. Parameters meaning some diameter of a pipe, distance between plates, pressure drops, which is fixed. Okay. So, those are the scales which we normally use for making a equation dimensionless, right. So, the origin of this method comes from dimensionless analysis. Okay. And so, in this particular problem, supposing I want to make the equations dimensionless, I have to make my u. Okay, here we choose characteristic scales for what is it? Length, time. These are the independent variables, length and time, spatial direction, length, time and velocity. Okay. So, in my problem, this Rayleigh problem that we are discussing, what are the characteristic scales which are available? For velocity, there is a characteristic scale, it is the velocity of the plate. Okay. So, u characteristic equal to u naught, this is the plate velocity, because the flow field is going to be determined by the velocity of the plate. So, that is my automatic characteristic choice. Okay. So, if I want to make velocity dimensionless, I will say u by u naught is my dimensionless velocity. Okay. So, u by u naught is u star dimensionless velocity. Now, what about the others? In the spatial direction, y, that is the only spatial direction, it is extending to infinity. So, there is no characteristic length scale. What about time? There is no characteristic time scale either. Okay, because there is no frequency, there is no, in order I can get time by saying, if I have a characteristic length scale, I can say characteristic length divided by characteristic velocity is characteristic time, but I do not have a length scale. Okay. So, I do not have in this problem, I do not have a characteristic length scale or a time scale. Okay. So, this problem does not have a characteristic time or length scale. Length it does not have, because everything is going to infinity, all the dimensions are going to infinity, and because I do not have length, I can't find time as something. Okay. So, now, but what we also know is that the only method by which this momentum is getting transferred from the plate to the liquid is by diffusion, momentum diffusion, not mass diffusion, momentum diffusion. Kinematic viscosity, mu divided by rho is the one which is responsible for the transfer of momentum. Okay. momentum transfer occurs by momentum diffusion, which is mu divided by rho, kinematic viscosity. And remember, kinematic viscosity has units of meter squared per second. Okay. So, this has units of meter squared per second, and this is the only thing which is by which the momentum is getting diffused. So, and diffusion is the only mechanism for momentum transfer in this problem. Then you know what is the time taken for in a given time t, in a given time t, the distance over which momentum diffuses is going to be given by L is going to be given by square root of nu times t. I mean, this is true of all diffusive processes. Okay, the momentum in a time t, what I told you, initially the plate is moving. So, when will at a particular time t, let us say 1 minute, the distance over which the effect of the plate will be found is square root of nu times t. So, in 1 minute it will be square root of, let us say 1 second, because we are talking SI units. So, it is nu. In 10 seconds the distance over which the momentum would have diffused is square root of nu multiplied by 10. Okay. You can see this meter squared per second, this is second, so it is meter squared meters. So, what is the distance? So, in 10 seconds it has the liquid at a distance of square root of nu would find the effect of this plate which is moving. At 100 seconds 10 times square root of nu will be the distance to which this momentum would have penetrated. Okay. This plate is moving, the effect will the length over which this plate effect is found is going to be given by this. So, this is one kind of a length scale which comes, but this is not a length scale in the classical sense, because the classical sense, when I spoke about length scale, I spoke about diameter of the particle, I spoke about diameter of a pipe like in Reynolds number, because that is fixed. This is a property, this is all only nu is my parameter, t is an independent variable. Okay, I have not used independent variables to define characteristic scales in the past. In the past I used omega, frequency of the oscillation, which is something which I can control, which is a parameter which I can control. Okay, here there is no parameter I can control. Okay, the only parameter I can control is nu. T is an independent free variable. So, I want you to understand this difference. In the past, when I made things dimensionless, I used parameters which I could change. Okay, radius of pipe, radius of particle. Here I do not have anything except for the fluid nu. So, I should not, I have never defined my dimensionless scales with the independent variables, but here I have an independent variable here t. Okay. So, this is not a proper this thing, but this has units of length. So, can we use this to scale length? Okay. I mean, that is the question, and in that case y divided by square root of nu t is a dimensionless variable. I do not want to call it a length scale, but I just want to say that y divided by square root of nu t, y has units of distance, square root of nu t has units of distance. So, y divided by square root of nu t is dimensionless. Okay. So, this is a dimensionless quantity. So, basically what I am trying to get at is u, the velocity, is a function of t, y, nu and u naught, correct. The velocity when the plate is moving, it will depend upon the properties nu, u naught is the only thing, and then time and y. So, now if I want to make, and when you write an equation, all the equation all the terms should have the same dimensions. Okay. You can't have one term with dimensions of time, another with dimension sense of length. So, all of them have to be dimensionally consistent. So, one way to do that, so if I want to make this dimensionless, u by u naught, this is dimensionless. If I am writing this as a dimensionless variable, the right hand side should also be in terms of a dimensionless variable. Okay. So, I am going to say, so and I found out that there is one dimensionless grouping G, nu and T. Okay. So, sorry, y, nu and T. So, I can write this as some function of y divided by square root of nu T. Why am I writing this combination? Because this is dimensionless. So, everything will be in terms of dimensionless variables. So, this is the motivation or the background for me to seek the solution in terms of this dimensionless group, and this y divided by square root of nu t and define as eta, a new variable. So, basically what I am doing in similarity transformation is I am trying to seek a solution not in terms of t and y separately, but I am saying that the solution depends upon this group y divided by square root of nu t. Okay. And I will now say, look, well, I will proceed, if such a solution exists, I will get a solution. If a solution does not exist, then I have to go back and do something else. Okay. So, we started off with making the equation dimensionless. We have but this making it dimensionless is different from the classical methods that we have been using so far. I want you to understand that, okay, because whenever I use characteristic scales, there were parameters in the problem which I could change, like diameter of the pipe, okay, gap between plates. They are parameters, but now this dimension, this is a parameter which I can change, the velocity with this I can pull. But here I can only change the fluid, but I can't change this guy, but this is a scale. So, this is some scale, but this scale contains time, which is an independent variable. So, I can't really control that. That is the reason. Why is this problem? Because this problem does not have any characteristic length scale or time scale. Okay. So, this is dimensionless. I am saying this dimensionless group, is it a function of this dimensionless group? So, that is the argument we are making. So, we are going to seek, if since this is a dimensionless group, is it possible to have a solution where u depends upon this combination of y divided by square root of nu t. Okay. The dependence of u is on the group y divided by square root of nu t. It is not, I mean it is on y and t, but I can look at the combination. Okay. So, if that is that is possible, then what I want to do is I would like to go back and look at, make a transformation, relate t and y, and in my differential equation convert everything to my eta. Okay. So, what I am saying is I want to treat this as a group, as a dimensionless independent variable now. This eta is my dimensionless independent variable, and which contains all of this, and this is my dimensionless velocity, and one dimensionless number, everything will be dimensionless. So, we seek u by u naught as some function of eta. Okay. Eta is dimensionless, u by u naught is dimensionless. Okay. And this grouping, now how did I come up with this? I used some physical argument. The distance over which the momentum is transferred for a particular time is square root of nu t. So, that is the length scale, length over which momentum diffuses. So, I use that to make my y dimensionless. Okay. And again I have a t, an independent variable in the scale. So, I can't really, this is not the usual classical way of making an equation dimensionless. Okay. So, now I go to this equation and I want to convert everything in terms of u to u star, this is u star is u by u naught. Okay. I want to convert this to u star and I want to convert my independent variables t and y to eta, because now my independent variable is going to be eta and eta has y and t both inside it. Okay. So, now this becomes u naught d u star by d eta times d eta by dt. Okay. This is the left hand side, du by dt, that is u naught d eta by dt times d u star by d eta. What is d eta by dt? I can differentiate this with respect to time, keep y constant. Okay. So, u naught times d by dt of y divided by square root of nu t du star by d eta, and this becomes u naught to y by square root of nu, this constant, d by dt of t to the power minus half, that is minus half t to the power minus 3 by 2, no. I don't think it's right. Yeah. Yeah, I did too many things. The numerator is minus. So, now what do I have? And this is equal to u naught times oh boy, let me do this properly, y by square. I want to take out t to the power half, I leave one t here. So, t to the power half, if I take it here, I will get eta, y divided by square root of nu t is eta. Okay. So, I have eta, I have a 2 and I have a minus half equal to minus half, okay, minus half, and I have a square root of t remaining. No, I have t remaining, I have taken off square root of 2, I have t remaining, du star by d eta. Okay. This is my du by dt. Yeah, makes sense. Du by dt is this. All I have done is differentiated. Okay. Now, I have to work on the right hand side. I work on the right hand side and I want to convert the u to u star again when u naught goes out, and I want to convert the y to eta. So, nu times d square u by dy square. So, this is basically differentiation. Okay. Is nu times u naught times d by dy of d by dy of u star. That is the second derivative, and this I write as nu by u naught d by dy, and what do I write here? Du star by d eta times d eta by dy. I am converting my independent variable from y to eta, because now it is eta. So, what is d eta by dy? 1 by square root of nu t. Okay. And I am differentiating with respect to y, so that is a constant, I can pull it outside, and again I have to convert this y to d by d eta. I will get again 1 by square root of nu t. Okay. So, this will give me nu times u naught times d square by d eta squared of u star times nu t. Okay. What have I done? I have just converted this d by dy to d by d eta. Another nu t will come, square root of nu t will come. That square root of nu t and this square root of nu t will give me nu t. Okay. I am not doing that. So, now I am really a happy guy because this nu cancels off, and I found out the left hand side. Left hand side has is this is the time derivative with respect to u, this is the time derivative with respect to y, and I need to substitute it here. So, I have minus half of u naught eta t. Now, I need to write this as d u star by d eta, okay, d u star by d eta, because there is only one variable for u star, only eta. So, it is not partial derivative anymore, okay, equals u naught by t d squared u star by d eta squared. Okay. And so, this u naught cancels off, this u naught cancels off, this t cancels off with this t. So, what I am left with is d squared u star by d eta squared plus eta by 2 d u star by d eta equal to 0. So, this is my ordinary differential equation for u star in terms of eta. Okay. U star is dimensionless, eta is dimensionless. Okay. And basically I have this ODE for eta. Okay. And what I will do is u star is same as f. So, I am just going to call this d square f by d eta squared plus eta by 2 df by d eta equal to 0. Now, one thing that you have to understand is my original problem had 3 conditions to be satisfied, 1 in time and 2 in space. After doing all this transformation, I have converted it now to a problem which is second order in eta. Okay. So, what does that mean? I need only 2 conditions for eta. This problem is a second order differential equation in eta. I need only 2 conditions. Original problem had 3 conditions. So, looks like I had an extra condition to begin with, because I had 1 initial condition and 2 boundary conditions for the original problem. Okay. But this problem has only needs only 2. So, what are these conditions is what we have to look at. Do I have to, how do I manage this? Remember, eta is y divided by square root of nu t. So, as y goes to infinity, eta goes to infinity. As t goes to infinity, t goes to 0, eta goes to infinity. So, basically what I am saying is eta tends to infinity as y tends to infinity and t tends to 0. So, my two boundary conditions were u equal to 0 at infinity and u equal to 0 at time t equal to 0. So, both those conditions are collapsing into eta equal to infinity. Okay. So, the two conditions, two original conditions at t equal to 0, u is 0, at y equal to infinity, u is equal to 0. Okay. Yeah. Give one condition, eta tends to infinity implies u is 0 or u star is 0. You understand? So, two of the conditions are basically in, when I am using my similarity transformation, two of the conditions collapse into one. Therefore, one more is remaining, that has to give me the second one. So, this gives me the condition as eta goes to infinity at y equal to 0. I have what is eta? Eta is going to be 0 for all times. Okay. U is equal to u naught or u star equal to 1 or f equal to 1. So, those three conditions which were bothering me, how am I going to let go of one condition and give me two conditions? I get this. Okay. So, basically I am now in a position to solve this. We can solve this, I mean we will do it in the next class, but you can get this, but you get a solution in the form of some error function, but the idea is what have we done? We have converted to a partial differential equation to an ODE. Motivation is characteristic scales were missing, okay, and we therefore were looking for a solution using a similarity transformation. Then we proceeded, and because at the end of the day I have an equation which only contains eta. Supposing after doing all this process I have an extra y or an extra t in this equation, that means what does that mean? It means I do not have a, I cannot use similarity transform to convert it to an ODE, because then this will depend upon eta and t. This equation is independent of y and t, it has only eta. Therefore, I am possibly on the right path of looking for a similarity transform. If this had a y, if this had a t somewhere sitting inside, then u star is a function of eta and t. What is the big deal? Again I have two variables. It is a function of eta and y, again I have two variables. So, that means similarity transform will not work. Okay. So, because there is only eta, I mean that means we should proceed further and get the solution. We will do that in the next class. Okay.